So, of course, this is the first meeting. We've all introduced ourselves. Meetings will occur weekly as of now on Fridays at 4 p.m. EST. We will typically try to meet once a week. And if during weeks or other things we need to talk about stuff, we will just do ad hoc meetings as needed. So first of all, just for everyone's benefit, we need to explain what pathology is. So the definition of pathology is the study of disease. In this particular project, we are going to be studying images, image slides, basically tissue slices. There are a lot of size constraints associated with the data that we'll want to talk about, and there's a lot of interesting stuff associated with it. The images are colored with something called hematoxylin, eosin, and sorry, my notes flubbed it. But the purple blue is the cell nuclei, and the pink is the tissue itself. So our data already differs from normal data in the real world, natural images basically, in that we have a extremely different set of data. It's also worth noting that in, quote, the real world, our data is a two-dimensional projection of 3D data. That particular tidbit will be very relevant when we get to approaches. Oh, there we are. So this is a much cleaner image. So the hematoxylin is the pink, or the other way around. We have the pink, we have the cell nuclei, and there's also relevant to us diaminobenzidine, DAB, which will stain things a brown color when you are specifically trying to look for that. One thing that's worth noting here, which will also be relevant later, is that depending on the lab and setup in question, the colors that you have will vary, independent of the tissue itself. So some of the stuff that makes this data cool or just interesting, but also, of course, difficult, is that it's gigantic. To give you some sense of scale here, a whole slide image could be on the order of 150,000 by 150,000 pixels. That's per side, as you can see near the bottom there. Your screen is probably something like 1920 by 1280 pixels. And if you took the entirety of a resized ImageNet, it would practically fit into one of these whole slides. So absolutely insanely large images. It might seem like a lot of data, and in some sense it is, but it's still very difficult to work with. And that's why quite a few people have already mentioned here how they're working on whole slide stuff. You can barely fit whole slide stuff easily into memory, let alone processing it for downstream learning like ML. Right? If we're using like a normal setup, something like Atom is going to be using 5x your parameters for just buffer and stuff. And between that and actually having a reasonable batch size, you'll go out of memory really quickly. So there's a lot of things that we need to figure out with that. The other thing that I find incredibly interesting about path data is that it's inherently hierarchical. So when you're at the like 16 by 16 level, you have cellular features. If you go up one level in resolution, you have cellular organization, then you have tissue phenotypes, and then you just have like most of your slide. The image that we're looking at was taken from the HIPT paper, which was a hierarchical image pre-training for path data. Really cool. I have the link in the notes if people want it. I definitely recommend taking a look there. But the hierarchical nature is neat, and relevant, and the fact that the data is gigantic, also matters quite a bit. So a normal question that would be asked, although perhaps not by the people here, but just in case you're on the fence, how can machine learning even help with pathology? Well, for starters, computational pathology is already a well-defined field. It's been proven academically. There's lots of benchmarks. There's lots of interests. Perhaps if you were here yesterday, Connor explained how there's not a lot of foundational fMRI models. That's not the case for pathology. There's at least like 12 plus different models that we know of, lots of interest, lots of people doing it. But of course, the reason why you might want to use computation for such a task is that the amount of data in the real world, but also the amount of data here, can vastly exceed what humans are capable of reasonably looking at. So if the blocker is the human ability to actually just scan images, then it makes sense to use something like machine learning, which has been solving, image problems in a reasonably effective manner for decades. And even if we only count since 2011 with AlexNet, it's still over a decade. So, okay, so what we have here is a non-exhaustive list of a bunch of the current literature. I'm sure that there's stuff that we've missed. If there's something that you particularly know of, please put it into the Discord channel. We can discuss. But these are some of the biggest and most recent models. This would be like our contemporary models, our peers, for what we're trying to create here. So the ones bolded at the bottom are, to the best of my knowledge, the most performant. One of the difficulties in the space in general is that nothing is standardized. Nothing even resembles standardization. For example, if you look at the number of whole slide images used by every single model, you'll notice that every single one is completely different. And even for the ones that are using an overlap, everyone's using their own secret private data. There's no standardization there. There's not a ton of standardization in model sizes, although recently we've been getting to something a little bit more clean. We'll get to the reason why in a moment. But it's really hard to compare these things, even if we take into account the fact that everyone's training on different data with slightly different architectures and slightly different hyperparameters. So the goal of this project, what are we even trying to do here? Well, the goal from a machine learning perspective is we want to achieve state of the art. We want to train models that are performant, not only in the academic sense, although we want to top the benchmarks, but we also want these models to be useful in the downstream. So that's one reason that I'm really, really excited that we have people here from like all stages of practice. So yeah, that's just the immediate goal. How we're going to get there, there's a lot of details. But we're also interested in things adjacent to just foundation models, like fast fine-tuning, and some other stuff that we'll get to later. Better evaluation methods, more standardization of the system. Yep. So I mentioned a few times stuff that would be relevant later. That's right now. The common approach is actually just a singular approach. Practically everybody is using Dino, just due to timing. Everyone's using Dino v2 for most of these models. For those of you that are not familiar with Dino, we'll discuss in a minute or two, but effectively Dino is a self-supervised model. This means that it trains on data without labels, and it forms a class of things called self-supervised learning. So everybody has kind of converged onto Dino as the answer. We're not completely convinced. We have interest in testing out other solutions, but I think it's impossible to deny that Dino v1, v2, and now of course v3 has come out. It's impossible to deny that these models are extraordinarily powerful, and at the very least, on the benchmarks that we have, they've proven themselves really good. In pathology also, of course, not just in natural images like you see here. So I'm going to briefly dive into what Dino is and how Dino-based self-supervised learning works for those that are not familiar. So at its core, as mentioned, Dino works without existing labels. This is where the self-supervised term comes in. This is because historically, and if we look at things like AlexNet in 2011, the ImageNet competition, and everything before that, it's really hard to learn from data when you don't have a clear task in mind. Classification, you have a label. Your goal is to train a model that is capable of recognizing what image class an image belongs to. So when you don't have that, you need to come up with like really inventive solutions of developing something that's capable of learning useful representations of your data so that you can use it for downstream tasks. So Dino falls into a subcategory of self-supervised learning called student-teacher. You can see that on the left-hand side where we have the student and the teacher model listed. The teacher model is frozen. It does not contribute gradients backwards towards the, it just doesn't contribute gradients backwards. You can see that with a little horizontal parallel bars there that says SG, that's for stop grad. And the teacher is also equal to a frozen EMA, exponential moving average, of the student. So what you have, the way training looks like, is, as you can see on the right here, you get one image, one large image, and you take crops of it. Just for the sake of the explanation here, we'll assume that it's two different crops. So the student processes one of those crops, and the teacher processes the other. The crops are also augmented. We'll discuss augmentations in a little bit, but our crops are augmented. The augmentations are random and different for each model. And then what we try to do is we try to match this CLS token between the two. So the reason that you need to use augmentations at all is because you need your model to be invariant to a variety of potential transformations. In the context of pathology, this could look something like the staining that was done. If you recall, I mentioned that staining is done differently from one lab to another. There's minor differences here and there. You don't want your model to be brittle in the sense that it can only recognize the staining that you trained on. It needs to be able to recognize a wide variety of things, a wide variety of options. This, of course, is real-world generalization, which is, paramount for these models actually being effective. So augmentations, very useful for that. We'll discuss that now, I guess. Just kidding. We'll discuss it next slide. So I wanted to briefly touch upon the CLS token that I mentioned, because I think this is like a really, really important component. So the CLS token was introduced, or at the very least was popularized in the BERT model. BERT was a language transformer, basically the first language transformer. So what you have is you have your sentence, or in our case, we would have a series of image tokens. And all of the image tokens are processed with self-attention. And you also just have this CLS token. Historically, the CLS token was used for classification tasks. But for our case, what it does is it's an attention sink. So we explicitly try to match the CLS tokens from the output of our teacher model and our student model. So what that means is that after your student and teacher have both processed these two different crops and different augments of the same image, we try to ensure that this classifier token of theirs has the same values in it. What this does in practice is it forces the model to cram all sorts of interesting and useful semantic information, a semantic overview of the entire image basically, into the CLS token. So there's also other ways of doing this stuff, but the CLS token is the recommended method of typically working with, I guess, the outputs from these models. So we briefly discussed augmentations, and I did just want to go over that a little bit more, because augmentations are, like, at least for the setup that we have, which is Dino-based, augmentations are extremely important. If you don't have augmentations, your model really doesn't learn much. It doesn't learn well. And even if by some chance you end up with something, it's going to be really brittle and completely fail when you try to deploy it. So augmentations and data, I guess, are some of the biggest components that is the biggest components in training self-supervised models. I don't think this is going to surprise anybody to learn that data is important, but pathology is no exception. Okay, so we've explained a lot, I guess, of the a lot of the history of the project here, some of the different methods. Did someone raise their hand?
Yeah, I mean, I had a question. I was just wondering, with the CLS token, are you just taking it from like the final pool layer, or is there a lot of experiments being done taking from, different latent layers, early layers, middle layers, later layers?
Yeah, that's a great question. Excellent question. So what you're describing comes up a lot in a few different places. It comes up in style transfer, and it comes up when you want to use a model as a perceptual loss, because it's not always necessarily clear where you should be taking the CLS token from. In the context of Dino, unfortunately, I don't have a Dino architecture in front of me, but in the context of Dino, we are explicitly designing our loss function between the two CLS tokens. So It hasn't been examined, but I suspect that in practice we would almost always find that the final layer output CLS is the most important one. Yeah. If we want to use, however, intermediate features from the rest of the tokens, maybe we want to look at different layers. So yeah, no, that's a good question. I'm not familiar with.
Just another thing, with these slides that you showed, are there reports usually as well in terms of training data, or it's just images?
What do you mean by reports?
I mean, as in, you know, a pathologist has gone through this and he's given his sort of analysis of the images. Like, did he find any problems with it, or, you know, essentially some analysis that accompanies the image data, or is it just the images?
Oh, okay. So the data, there's two different things in question there. One is the data that we train on, and one is the data that we evaluate on. So we'll be discussing evaluation data in a little bit, and I'll come back to your question then if it has not been answered naturally by the presentation. But in terms of training data, the training data has no labels. It has no pathologist well, we are not using any of the pathology information associated with the data. What we've been training right now has been purely on TCGA, because TCGA is a public data set that anybody can use. And we want, of course, something that can be standardized, that anybody can replicate what we're doing, like easily, cleanly, and openly. But we are only using the images themselves from TCGA right now.
Right. Thanks, Daniel.
Yeah. Yes, question?
I'm curious, how do people usually like embed these images? Do they just do like per slice? Because I know like usually the images are like a stacking of all the slices, and then you have like this kind of three-dimensional tensor.
That is a great question. Let me think if we answer that. No, we don't naturally answer that in the slides. Can you hold on to that and I will come back to you and answer?
Sure.
Okay. Yeah, we'll get there pretty soon. Or maybe we can do it right now. I'm trying to think. Okay, so our focus this exact moment is we want to leverage Dino v3 without using a full fine-tuning methodology to try to get state-of-the-art results. That's something that we really would like to try to do. We did some super preliminary experimentation with Dino v3 when it came out. That was like 2 weeks ago now or so. I think it was like 2 weeks ago yesterday. So we did some experimentation with that. Or maybe it was 3, I don't know, it doesn't matter. It was very recently that it has come out. All of the previous models that we mentioned were either trained on Dino v1, a couple of things were trained on iBot, and I think at least HIPT was trained on a just pure VIT style. So we would love to play around with Dino, and part of playing around with Dino will include what the previous person just asked about, which is how we train on the data itself when it's so high res. But we've had some incredibly promising early results, and we want to leverage those, expand on it, and see how far can we push this sort of minimal training or not full training Dino v3 models. So to answer, I guess, the previous question in some part, one of these secondary focuses that we've had was we want to make a working reproduction of the Midnight 12K paper. Let's just go back super fast. So if you see here, there's Midnight 92K and Midnight 12K. Midnight 12K was only trained on TCGA. So that basically makes it a pseudo benchmark for an open source replication. Unfortunately, Midnight has not released their code nor their models, or they released the models, but they haven't released the code or the training methodology. So it's not fully there, but that's what we're trying to get to soon. Hold on, let me. Okay.
Also, just like generally speaking, what everyone does is, they take the giant whole slide image and then they patch it right into 224 by 224 patches, and then those can be just like randomly at different magnification levels. Exactly.
More specifically, I think, so people usually take 256 by 256 because it's a clean power of 2. Then they resize it to 224 by 224 or randomly crop it. It's not entirely certain what Midnight's doing there yet. And as Paul said, it's grabbed at multiple magnifications. Does that answer that question, or do you have more thoughts?
Yes, thank you.
Okay, wonderful. So there's so those two things basically our current focus is Dino v3 and the midnight reproduction. There's a lot of different ways to contribute to this effort. That will be, I guess, the focus of the last half of this presentation. But we have some ideas, for example, that I have started, but the code for them is not complete, and we're going to need some debugging there. We have a bunch of different ablations that we want to run on different methods of working with these models. We have a lot of work to do on EVA. So we are evaluating our models at this time using Kaiko's EVA repository. We've created a custom fork of it because we needed to make some changes, and we will go over that repository soon. So Kaiko's EVA offers a lot of different options for how you can evaluate these models. It's a reasonably robust framework setup where you can plug a model in as long as it adheres to the correct forward method implementation stuff, returns data in the exact tensor shape expected, and yeah. So some of the tasks that it can do is there is classification of tiles, whole slide level classification, and segmentation. To answer a previous question, these images, when we are doing evaluation, those have been labeled. So there's actual labels on, like, is this a benign tumor? Is this an invasive tumor? Is this not a tumor at all? Stuff like that. And unfortunately, every single benchmark basically has its own different set of labels, but the labels are all, pretty well lined up. So just following up a little bit on what I was saying a moment ago, we were playing around with Dino v3 using EVA baseline. At its core, what EVA does is it does something called a linear probe. So what this means is that you take your output from the Dino model. It's going to be a CLS token. So you have your single CLS token for your patch. Your patches could be anywhere from naturally 224 by 224. Bach dataset is like 2048 by 1700. The images get resized to 224 by 224, run through Dino. We take the CLS token, and we just train a linear layer after that. So it's basically just trying to test the linear separability of your embeddings. And that is the default Kaiko method. So we will go into more detail on what else we've tried and why we want to try it. I have the information for that is in some of the code base, so I don't want to make it redundant there. I did want to, however, just bring the next steps up in case so that people know what the future looks like. We want to look into high resolution models in some capacity. As everyone here is aware, your data does not come to you in the form of cleanly designed patches. It comes to you in a giant slide. So it's kind of important that you have models that can work with the slides themselves. We would love to play around with different methods of self-supervised learning. That might include grabbing CLS token, but also, different parts or outputs of different layers of the model, as was asked. Lots of different things to play around here with how we are evaluating and working with, like, the models that we've trained. And of course, different methods of training these models, different SSL. So now we are going to go off to the code base. Or we'll go off to the code base in a minute to describe exactly what contribution could potentially look like. And we'll go from there. Yes, someone has a question.
Yeah, so you mentioned that you evaluated using EVA. I was curious,
Yes.
what dataset did you evaluate it on, and what were the results using linear probing?
Yeah, I have my exact results listed somewhere else. So what we were doing is we were evaluating, hold on, let me pull it up. It's on a different screen, unfortunately. We were evaluating Dino v3, no fine tuning, just baseline Dino v3, linear probe on Bach and CRC were the two data sets that we tested on.
Okay. And I was just curious what were the results like, because I also linear probed a lot of foundation models and benchmarked them for one of my papers. So
got it. So just so you know, this is Dino v3 not tuned, right? Yeah, okay. I'll have to get back to you on the results. They are not in the spreadsheet I thought they were, but for reference,
no problem.
Hold on, let me see what I can remember. Just from memory, Dino v3 pure linear probe achieved a 0.759%, 0.759 accuracy on Bach, and Kaiko's EVA Midnight 12K is a 0.907. I think their 89K was actually slightly worse there. We weren't able to evaluate on every single data set because almost none of them are actually implemented or downloaded by default in EVA and have like, separate requirements. CRC was also, I think, pretty good. I want to say that CRC by default with Dino v3, this is the 7B model. I want to say that it was around a 92% accuracy, but I think CRC is just generally pretty easy, especially because average performance for everybody is like 92% baseline. So.
Yep. Okay. Interesting. Thanks.
Yeah. How were you evaluating other foundation models? I'm just curious.
Oh, I just did exactly the same as Daniel said. I also just trained a linear layer over the CLS token. And I think I evaluated like 6 of the pathology foundation models. And with linear probing, the results were like kind of really bad, but I was also evaluating not just the accuracy, but I was evaluating balanced accuracy. So, sorry, what?
Sorry, what was the metric that you were using?
Balanced accuracy. It's the average of sensitivity and specificity.
Got it.
Yeah.
Okay. No, accuracy alone. So accuracy is really nice for Bach specifically because Bach is balanced. But for everything else, it's whatever.
Yeah. So my data set specifically was like really imbalanced, and it was also kind of like a tougher task, I would say, because it was classification between atypical and normal mitotic figures. So yeah, balanced accuracy was a better metric there. But they performed like really well. Really bad with the linear probe. Like the balanced accuracies were all in the range of 0.56 to 0.65. But when I used LoRa on the same foundation models, they like vastly improved the balanced accuracy. I think it got up to like 0.85 or 0.86 or something like that on the same data sets.
Okay. We'll definitely have to talk to you about that at some point. LoRa is one of the methods that we are considering for non-full fine-tuning of Dino v3. So that's hardly a surprise, I suppose. There's not so many PEFT methods. Yeah. Okay. So does anyone have any other questions? I guess we might as well discuss like presentation and related things now, and then we can go into the code base.
Yeah, sorry. I had one question. I just want to, again, I mean, I think this was more on a high level, and I'm new to this field, and I was just, honestly, whatever I know is through ChatGPT questions and answering. And the sense I got is that, these models are being used in the industry today. So I guess what I was trying to understand is what is being used in the industry, what are they open to right now? And from what I gathered is that there's a lot of private companies with the they partner with the hospitals, get their data, train it on it, and then that gets used. Do you know if any of these foundation models are being used in the real world today?
That's a great question. It's not. So I don't have any intimate knowledge of what is being used where. But you're definitely correct that a lot of these things are from partnerships. In fact, almost all of them are partnerships. And there are, people also have their own hidden models or models that they only discussed at the very, very high level. Like Optimus, for example, is trained on private patient data, and it's almost certainly being used by the people that I guess provided the data with some sort of like partnership there. But anyone that's not only training on TCGA is training on private data and probably partnering them in some capacity.
Cool. Thanks.
Yeah, unfortunately, I don't personally have a lot of further insight into how the models are being used privately. If anyone else here knows, please speak up. But
yeah, I mean, part of it is like obviously there's a yeah, I mean, I think it's very early on still with the foundation models, so it's hard to it's still unclear what are the I mean, it's still like a lot of work left for this, but also like some of the models are being used, like prop packs, for example. I think there's some people are using it for different like clinical applications, and of course, there's lots of like pharma applications, and so some of these companies are developing foundation models in pathology to apply for pharma. So like Path AI, I think, for example, is very much focused on it. But yeah, I think it's still kind of like a lot to do in the future to get it to actual applications.
Yeah, so I'm just curious also. I mean, you're talking accuracy about 0.79. Do we know what, like, if a pathologist was to do it, what is their accuracy and what is their expectation for them to be able to use something like this? What are they expecting it to be?
Yeah, that's a good question. I think that depends heavily on the tasks, because there are some tasks where there's less concordance between pathologists and other tasks where there's a lot more. So I think it kind of depends specifically on the task at hand. I don't remember what that is for the task that Daniel was talking about. But yeah, it kind of just, yeah, it just depends on the task. But yeah, I think that's just, yeah, it's highly dependent.
so
Yeah.
that's a small note also, is that the models don't even have to be perfectly accurate to be useful for pathologists. In fact, I think it's pretty arguable that because it really depends on how you want to utilize these models. If you want a model to entirely replace your pathologist, then you need it to be like nearly perfect. Or that's just how it is from the usability perspective. But if the model is intended to augment a pathologist, then the question becomes not how accurate is the model, but how much time can the model save? So even if you have like, let's say the previous person's atypical thing, even if the model is only relatively low on accuracy, as long as it is capable of grabbing some stuff that a trained medical professional can take a look and be like, ah, yes, that's cancer there. It saves time. It can catch things that people missed. So it's not only, hey, was this able to operate by itself? For benchmarking purposes, yes, you do typically just look at it in isolation, but it's a lot more complex when you want to deploy things. So
yeah, that makes sense. Thanks.
I mean, there's also like tasks that pathologists cannot even do. Like a lot of this, so like one of the good examples, like all this prediction of molecular and genetic information directly from the slides, which is again a huge time saver if you don't have to set it out for lab tests and things like this, but you can still get some sort of analysis just from the slide. And that's something like a pathologist cannot do directly. And so like these are sort of, I think that's also like the real advantage here is like not just like doing tasks that pathologists can already do, but also tasks that pathologists aren't able to do, but the AI is able to pick up on unique features in the images. And that is actually like a kind of a value add in terms of like this isn't possible before. So that, I mean, that's a different question, of course. Again, like, yeah, what is I mean, I think even the question about like what the performance is for that's needed for it to be useful is also a completely different question as well. So that's another thing worth noting.
Yeah, no, that makes sense. Thanks.
Absolutely. No, that's great. Okay. So let's well, hold on. Before we finally go into anything else, does anyone have any other questions? And we can obviously come back to as needed, but
Yeah. Oh, sorry, I have a question. So I wanted to ask, like, how do you do the augmentation in terms of, if you're using Dino? So what does the augmentation look like for pathology?
In terms of what?
Data. Considering you're using Dino, right? And your presentation, I saw how you like is a different augmentation. So I'm wondering how data augmentation looks like in on pathology
pathology.
slides.
Yeah, that's a great question. So let's see. Maybe if we have time at the end, we'll go over it in the code. But for now, I'll just give you a by word overview. We'll stick on this slide for now. So it is possible to decompose your image from RGB space to HED space. The three different staining types. This can be done, I guess, mathematically using a deconvolution kernel, and then you can reverse it using a convolution kernel. So what you can do is you can convert your image into basically the channel strength associated with each of these stain components, and then you can just modify those directly. This is called I guess it's just HED augmentation is the term. We have that in our code. It was introduced pretty recently by Midnight. So that's the primary method that people have come up with that's been beneficial. There are other things like Randstain NA and a few other things but their efficacy remains like indeterminable based on more recent research. But the answer to your question basically is you augment it for the most part similarly to how you would augment natural images. The Dino pipeline has a really wide array of things that it modifies. Again, we'll go into that in the code if we have time at the end, but they do like solarization, messing up with hue, messing with contrast, all of these sorts of things. And you follow a similar pipeline, but not exactly the same, for augmentations for pathology imagery. We had to play around with them because the natural image space in some ways has a lot more variance in terms of just color than our pathology space. So augmentations that are reasonable in one are not necessarily reasonable in the other. And if you don't play around with that, you end up with stuff that's just like very clearly garbage and not useful. But the augmentations for the most part is similar minus solarization and plus a few other things.
Okay.
Yep. Okay, if there's any other questions, speak now. Otherwise, we'll have to come back to them later.
Hello, can you hear me?
Okay, excellent. So as mentioned earlier, one of the things that we want to focus on right now is evaluating Dino v3 and figuring out what's basically the limit. Yeah, question?
Can you hear me?
Yes.
Oh, sorry. Can you go back to the sheet that had a bunch of data sets?
Yes. What slide?
You had the Google sheet that had a bunch of data sets, right? I just joined midway. So
it had a bunch of the models, the different models, the recent models.
Oh,
okay. Yes. Okay. I was like Google. Yes, this is pasted from Google Sheets, but yes.
Okay. All right. Sounds good. All right.
Oh, was that?
I just wanted to see it.
Of course. So slides will be shared with everybody at the end, and you can take a look there.
Okay. Thank you. All right. Sorry.
Yeah. You don't have to worry about not being able to access this information in the future.
Okay.
Did you have a question about this, or you just wanted to look?
No, I just wanted to see it. So.
Okay. Yeah. We'll send that over. Don't worry about that. Okay. So one of the problems that we found with EVA is that while it technically implements every single data set, most of the data sets are not downloaded automatically, and it requires somebody to do it by hand. In particular, I was working on getting a few of these, and it was surprisingly difficult. So that's one of the best ways to get yourself, I guess, if you are new to the space and would like to help contribute, this is something extremely valuable. We need all of the data sets available, usable easily by anybody that wants to be evaluating these models. Otherwise, what we're doing is not really reproducible, And actually, we found that with one of the data sets here. I cannot remember which one, but one of them is just not even available anymore. I'll say it was Concept. Yeah. Concept is just listed as cannot be downloaded. So we would like to make sure that we have access to all of the data needed to evaluate fairly against everybody else. And one of the data sets, that's one of the data sets that just doesn't exist. A few of these issues are associated with data sets, and we need help getting those downloaded. So that's one of the ways people can contribute. One of the ways that people can contribute relates to Dino v3 nonlinear based overfitting. So actually, for this to make sense, let's very, very briefly take a look at a super simple implementation within EVA of what a linear probe would look like. And I think that this will help explain some stuff to people. So also, I believe that this repository is public. So if you want to go take a look at the code on your own time, feel free. Or you can follow along, whatever. So if we recall, EVA expects that your foundation model will output a tensor of the shape batch size, comma, 1, comma, embedding shape. 1 refers to the CLS token here. And the default is training a linear model, just a pure linear model, linear separability, only the linear layer here. So one of the easiest and simplest ways to potentially improve upon that is to normalize your data and then train a linear. This is important because our training process is somewhat stochastic. We have a limited batch size. There's effectively infinite orders of the way you can fine-tune your linear layer on your data. There's a lot of different configurations that you can do with weight decay, learning rate, batch size, all of this stuff. So lots of different things to play around with and tweak with. And of course, one of the easiest and simplest ways to potentially improve things is to introduce a non-linearity. So that's what we have here, is a very, very simple module for computing batch norm or RMS norm followed by a linear layer. And this is based on how Dino v3 was doing some of their linear probes. It does technically stretch the definition of linear probe because it's explicitly nonlinear, but whatever. The spirit of only training one layer beyond is there. So this is the basic setup. Now, one of the most obvious ways to think about this is, hey, we are only using the CLS token. The CLS token is a semantic overview of our image, but we're not training on data that Dino is familiar with. Is this semantic token really the most effective way to capture our data itself, especially given that, you know, it's a different type of data? So this introduces a potential method of working with the data, which is we use all of the outputs from the model, not just the CLS token. So this is all 196 patches. This is the 4 register tokens and the CLS. So that gives us 201 tokens. And again, usually you work with 1. So problem. What you have here is you effectively have this subspace or this manifold dimension, depending on how you want to define things, that's like 70,000. Because we have 201 times our embedding dimension. If we're using the VITS, the smallest VIT imaginable, the embedding dimension is 384. So that gives us 70,000. And when you train on all 70,000 features, what we found is that performance goes down. So the best theory for that, which is supported by some of the further tests that I've run, is the model is really, really overfit. So we would like to figure out, is there a way to use all of our features effectively while not overfitting the model? So the way, if someone was interested in picking up this task and working on it, what they would do is they would create some sort of version of batch linear located here. They would create one that operates on all of the tokens instead of just the 1 token. Maybe that would look like a concatenation, for example, where you just concatenate on the feature dimension. Maybe you have some sort of special thing in mind. I don't know. We can discuss options in the channel or just later on. But you would create something like this, and then you would run training. And we would go from there. So we have tasks at a variety of different levels of I guess, of compute required. I understand we understand, of course, that not everyone has access to an industry-level compute. You might only have your local GPU, or you might be on Google Colab, or any of the above. We have different options for different levels of compute, different things that people can start out with. So if someone wanted to do a nonlinear overfitting method, but they only have the compute to write code and test that it has a forward-backward going successfully, just 1x, even with a very small batch size, that can be sufficient, right? I want to be super clear that if people would really want to help, but they can't do stuff locally, Medarc has the ability to provide compute. We just ask that people help demonstrate their, I guess, dedication to working with us properly by picking up some stuff and working on it. So the way we expect that part to work is, ideally, what you would do is, if you're interested in picking up an issue of some kind, you will mention, right now you can't be assigned an issue because not everyone is on the repository. Talk to me and we can get you added and stuff. But what you would do is you would create a fork of the repository. That's right here. You'll press the fork button. You'll fork the repository. You'll create a new branch for whatever feature you're implementing. Let's say that you are implementing this one that we discussed. That's right here. So you want to implement this one. You'll create your code. You'll test your code. Again, one forward, backward, or we can talk about it depending on the task in question. You'll open a pull request from your repository to our repository. Just one small thing to note is that pull requests by default go to the parent, the uppermost parent. Because our repository is a fork of EVA, you'll need to modify that before you just press the submit pull request button. But you'll create your pull request. We have an example one here that we're going to go over. So you create your pull request, you submit it, and then we merge the code, and then we'll discuss how people can get access to compute and contribute further. So that's basically the super duper high level of like some of the stuff that we want to do. Sorry, we have all these issues. We have a bunch of them for data sets. We have some stuff for different methods of mitigating overfitting. We have some stuff for different methods of processing the high amounts of data unrelated to overfitting. We want to try pushing the boundaries of what we can do without training for a little bit. And simultaneously, we're also going to be working on some stuff for very light training, similar like Laura and friends, as discussed previously. I don't want to go very, very deep into code or like coding practices, but we have all of this, all of the contributor guidelines are available online. It should be clear, but if there's questions, please post them. So what you'll do is you have your pull request. In this case, it's from another branch. Your branch should be named appropriately. The name of the pull request named appropriately. You'll have a commit telling what's going on, and then I'll review the code and we'll merge it and done. Very clean, very easy. Okay, so before I dive into how EVA itself is run, which will be relevant for like a lot of our focus right now, does anyone have questions on anything we've discussed recently? Or I guess just in general?
Maybe I can just give a quick recap maybe of where we're currently at. Thank you, Daniel, for obviously walking us through all this. So at a high level, right, like there are a ton of computational pathology foundation models that have already been released. Almost all of them have been trained on DynaV2. You know, they fine tune it on their own data sets, and then they put out papers and show how good the models are. In practice, we want to immediately capitalize on the latest DynaV3 model, because you can imagine that if everybody was using DynaV2, there's an easy potential win if you switch to using DynaV3. And so that's the sort of most immediate action that we can take as a sort of community-based project that can potentially be used even without full fine-tuning initially, which is kind of the promise from the authors of the DynaV3 paper. It's kind of impossible to do anything with DynaV3 if you can't evaluate it, right? And that's why there are some papers like Kaiko's group putting out the midnight paper, they have this framework called AVA that Daniel was talking about. In practice, you can't actually use it, right? We try and use this framework and figure out that it's not really usable unless you do a ton of manual tweaks to it. And that's why a lot of the tasks that we are hoping people can get involved in are just fixing AVA. And then we can have an actual framework that can be used to compare what we're doing to existing works, many of which have released their model weights. We can do direct comparisons that way. Beyond that, we want to get DynaV3 working for use as a probe, interfacing with the AVA framework, and starting with the linear probing stuff that Daniel's already done, expanding that to maybe more complicated probes, doing PEFT, doing more kind of fast fine tuning, and seeing what we can get out of that. And so there's a lot of different kind of tasks that we can do in parallel to get all this to work. Different kinds of probes, different sort of ways of approaching fine tuning DynaV3, as well as just getting the base AVA framework operational across all of the data sets, for which there's like over a dozen. So there's plenty of different kind of independent tasks that can be worked on as a group.
Thanks, Paul. Yeah, absolutely. Paul has explained it, I think, perfectly well. Okay. So I guess if no one has questions on just like this part of it, and I know we're delving into like super gory details here of exactly how anything will work. I'm delighted to talk at the end with people at a higher level than this, but I think it is beneficial while we're all on the call together to discuss what contributing would look like at the most basic level, right? Because everyone here is interested in some capacity in what we're doing, and if you want to be an active contributor, we want to make sure that things move cleanly for everyone. So there's not running EVA itself at this point is very simple. Some small notes is I highly recommend that you only run it on a single GPU. If you have multiple GPUs, you're probably familiar with the environment variable CUDA_visible_devices. Some of the data sets that I was able to test, like CRC, explicitly do not work if you have multiple GPUs available. So fun fact there. Now you will not have to debug that the way I did. But what you do is you just call EVA, EVA predict typically, and then you'll give the just give the configuration file that you want to work with. The config files are relatively straightforward, and we have one here. This is grabbed from the config folder and modified for our particular use case. In particular, if you are familiar with EVA, you'll notice the differences start around here. We've introduced a new wrapper which grabs a model from a local repository, in this case, the DynaV3 repository. This is necessary because DynaV3, at least as of the last time I checked, is not available publicly on Hugging Face or anywhere else. You need to sign a custom agreement with Meta in order to access it. So they might change that in the future. That did happen for DynaV2, but for now, this is what it is. So that's one of the things you'll need to modify is you'll need to modify those lines and here, these three lines. And none of the information that I'm discussing right now is like, not going to be repeated. I'm just going over it here, and we'll put all of the documentation properly in channels and elsewhere so people can work with it. So you'll set your class path to the new class that you've created, your simple class, and you'll modify the input features. And that's all you need to do. Launch is relatively clean and straightforward. Okay. So I think that covers most of what I want to discuss here. I hope this gave people a decent understanding of like what we're up to and what we want to be doing both now and in a little bit of the longer term. So let me know if you have any questions or any thoughts. Okay. So I guess if everything is clear to everybody, then we can just discuss things on the channel as people are interested. if there's something that you want more information on, any particular tasks, or if there is, you know, if you need more information, more clarity, or you just want to pick something up, we can discuss it on the channel then. Okay.
Did someone raise their hand? Did someone raise their hand? Did I miss it? No? Okay. Great.
Okay. Sounds wonderful. Talk to you all later, and thank you for coming.
Thank you, everyone.
Thanks, John.
Okay.
You too.
Yeah.